So you have a machine that has as input blargs, which are B, and as output furbles, F. Moreover, the number of furbles that you make, given a particular number of blargs that you put into the machine, e to the 2b minus 36 e to the b plus 8 times b plus pi cubed. Now, you're working to determine the current input. In other words, finding the number of blargs b. But most of the monitors on the machine are broken. There's only one that has a reading. And the only thing that you can see about it is it says there are 88 furbles per blarg squared. And the question is, what is b? Okay, so that's the problem. All right, now, you're probably thinking, what is a furble? What is a blarg? Do we care? No, you don't have to know. These are made up words. So you might say, okay, so then what's the point? Well, because I wanted to give you something that you hadn't seen before. Because oftentimes you think about things not in terms of like what's the real process, you just have sort of knee-jerk reactions. And we wanted you to think about things. So let's not focus on the 88 for a second. There's something here. There's units attached to this. Furbles for blarg squared. The units are telling the story. What do the units tell us? Sorry, what? It's like acceleration. So why do you say like acceleration? Right, it's like over something squared. So you can work by analogy. It's like, well, what if it was like furbles were meters and blargs were seconds? And it's like meters per second squared. So you use the word acceleration. What's another thing we could call it? Second derivative. So the units tell us second derivative. And now we go and say, oh, well, we have a reading for the second derivative. So in particular, this problem is really telling us f double prime of b equals 88. Find the value for b. So that's the problem. All right. So this is one of my, I wrote this, by the way. And this is one of my favorite problems insofar as how do you test people on units? And so it's saying, could you figure out, it was asking about a second derivative. Okay, so now that we've rephrased it, what do you do?
Take the derivative twice.
Yeah, we're going to take the derivative twice to find f double prime of b. So, does it matter that it's b and not x? Can we still take derivatives? And the answer is, it doesn't matter that it's b and not x. We can still take derivatives. No problems, no problems. All right, so we begin. F prime of b. And again, if you're not comfortable with the b, just think in your mind, well, what if it was e to the 2x? What would it be? And then just translate back and forth. 2e to the 2b? That sounds pretty good. Where is the 2 coming from? Chain rule. All right, how about this? E to the b. What's the derivative of e to the b?
E to the b.
Sorry, what?
E to the b.
B e to the b? It's e to the b. So the derivative of e to the x is e to the x. So when I say the derivative of e to the x, what we're really saying is the derivative of e to the x with respect to x. We oftentimes remove the phrase with respect to the variable. But in our case, now we're taking the derivative of e to the b with respect to b. How about the derivative of 8 times b? 8. How about the derivative of pi cubed? 0. Yeah, it's not 3 pi squared, it's 0. It's a constant. All right. Now, if you had not understood the problem and said, oh, take the derivative and set it equal to 88, would it have worked out nicely? Actually, it would, because I was very devious. I made it work out so the derivative also gave nice answers too. Oh, that was back when I was evil Steve. But now I'm nice, gentle Steve. Okay, so second derivative, f double prime. Yeah, so the 2 stays there, and then we're going to get another 2 coming down, yes? So 4e to the 2b. And then the derivative of e to the b. Still e to the b. The 36 is a constant, just comes along. And the derivative of 8? 0. So we found f double prime of b. We'll set it to 88. Well, this says, let's move everything to one side. And there's a secret here. I didn't write down the hint, so I'll write the hint down. This problem had a hint. E to the 2b is e to the b squared. True story, true story. If you multiply e to the b times e to the b, that is e to the 2b. So, we have 4 e to the b squared minus 36 e to the b, subtract 88 equals 0. Okay, what are some things we can do to make life nicer? Okay, we can substitute a name. So if you're comfortable with sticking with e to b, you can stick with e to b. And if you're not, then you say, you know what? Let's just give something a name for a moment. And math works a lot using this tool. So a lot of good math is done by saying, I'm going to call this thing a different thing. I'm just going to give it another name. And the further on you go in math, you're like, wait, all you're doing is you're just calling that thing something else. Like, yes, that's it. Isn't it cool? What do you want to call e to the b? X? All right. I thought you were going to be exotic and choose like y. But okay, we'll go with x. It's just a symbol. Is there anything else we can do in the meantime? Okay, so we can also factor 4. So we'll do it in 2 steps. 4x squared minus 36x minus 88 equals 0. Everything is divisible by 4. X squared minus 9x minus 22 equals 0. So, does this factor? So if it did, and I'm thinking it does because I hope I wrote the problem so it can be factored. What are you looking for? 2 things that multiply together to give you 22. One of them is positive, one of them is negative. And their difference is negative 9, right? Or one of them is positive, when you add them up, you get negative 9. There's not a lot of ways you can write 22. What is 22? 11 and 2, right? So if there's any hope, it's 11 and 2. Which one should be positive? Which one should be negative? Positive 2, negative 11. So x minus 11, x plus 2. Let's check. X squared, good. 2x minus 11x, all right. And minus 22. Okay, so, we've got 2 answers. X is 11, or x is negative 2. But wait, remember, this was a name x. So we put back what the name is. E to the b is 11, or e to the b is negative 2. Now, it's possible there could be 2 answers, and we can't distinguish. Is one of these a non-solution? Negative 2 is a non-solution? Why can't e to the b equal negative 2 be a solution? Oh, we've got a standoff here. Like, I want to explain. No.
Is it because it would then be a fraction? Or no, it would be a square rooted. No.
No, don't worry. No one's looking at you. You're going over all the logs of your previous courses. You're like, okay, where have we seen something? As you review your mathematical logs, you're like, okay, what have I seen before? Oh yeah, there's like log stuff, right? But a nice fact to know. Can e to anything ever be negative? Not in our class. So this is impossible. Now you're probably like thinking, not in our class, Steve, that sounds ominous. Well, there is a part of math where it's possible. But let's just say it gets a little bit complex. And I'll leave it at that. Okay, so that leaves just e to the b equals 11, but we probably want b, not e to the b. So how do you finally find the b? Natural log. So b is the natural log of e to the b. So that's natural log of 11. And so we have natural log of 11 blargs. That's how much is going into the machine at this point in time. All right, good times. Fun problem. All right. So that was that one. Yeah, know how to deal with units. Usually we ask you to give units, and the rule of units are you do what you expect them to do. This one gave you units and you had to figure it out. But other than that, no big surprises. Okay, here's one with the rate of change. Suppose you have f of x is ax squared plus bx plus c. Find the constants a, b, c. So the following is true. Now notice we have three constants, and it gives us three things. Now basically, what you should think of is if I'm trying to find three constants, I need three pieces of information. If I'm trying to find two constants, how many pieces of information should I be looking for? Two. And so if you have a problem on the exam, theoretically, where it says, oh, find A and B. So it's like you have to find two things. Then you should think of like, I need two things to be true. And start thinking about what two things you need to be to make things be true. So just keep that in mind. And I will say, I, for one, am a person who really likes problems. Find A and B. Many years ago, I had somebody from the engineering college come and say, your students can't solve two equations and two unknowns. So I've just been drilling my students now. It's like they will, as Newton as my witness, my students will know how to solve two equations and two unknowns. And so I hope that you know that. All right. So here we go. We have our list. F of 0 equals 10. Well, let's see what that tells us. If f of 0 equals 10, what does that mean? It says that when you plug 0 in, you get 10 out. Okay, so that says a times 0 squared plus b times 0 plus c, which, by the way, simplifies to what? C equals 10. Well, that was pretty quick. It makes me wonder why they had that condition there. But all right, fine. We'll give it to them. So f of 0 equals 10. We've already found c. We've already gotten points. This was an exam problem. We probably just got like 2 points. And you're probably thinking, yes, but it's out of 10. Well, yeah, but that's better than 0 points. Every point counts. All right. Average rate of change. When you see average rate of change, what do you think of? It's like the slope formula. So these are slopes. So you say, okay. So the first one, so in particular, I'll say it's f of b minus f of a over b minus a. It's the slope between the points a comma f of a to b comma f of b. So, all right. That being said, we say what? Well, we have this x equals 0 to x equals 5 is negative 2. So we have f of 5, subtract f of 0, divide by 5 minus 0 equals minus 2. Now, do we know anything about, let's see if we can extract some information. Do we know anything about, say, f of 0? It equals 10. Cool. So this says f of 5 minus 10. Now, on the other hand, multiply across, because I can multiply 5 across, equals what? Minus 10. Because I can multiply the 5 to the other side. So what does that tell us about f of 5? It's 0. Now, what's another way to say f of 5? Well, you plug in. So you get 25 times a, that's ax squared, where x is 5, plus 5b, plus c, but here we already know c is 10, equals 0. And if you want, you can divide through by 5, you get 5a plus b plus 2 equals 0, or 5a plus b equals minus 2. So here's a formula involving a and b. That comes from our second bullet point. All right. Are we ready for our next bullet point? So average rate of change from x equals minus 2 to x equals 5. So that would be f of 5 minus f of minus 2 divided by 5 subtract minus 2 equals 0. Well, that tells us what about f of 5 versus f of minus 2? Yeah, f of 5 has to equal f of minus 2, because when you subtract, you have to get 0. Do we know what f of 5 is?
0.
How do we know f of 5 is 0? Because we said it equals 0 over here. Right, exactly. Do we know another way to write f of minus 2? Well, plug it in. What?
Let's say 5a plus b.
Well, that's minus 2 is 5a plus b, but f of minus 2. We could do 5a plus b squared times, that's a bold move. But let's just plug in negative 2 first and see. And then we try it the other way. Negative 2 squared 4a. And then b times minus 2 is minus 2b. And c is 10. Well, okay. We can divide by 2. We get 2a minus b. And if we move the 10 across, equals negative 5. So there's another relationship. We need 2a minus b to be negative 5. All right. So we are to that point I mentioned before. 2 equations and 2 unknowns. So the point here is plug in. Know what average rate of change is. Average rate of change means slope of a secant line. You know, you're connecting your 2 points. By the way, what's instantaneous rate of change? Derivative. And so if you see slope of a secant line, that just means you're connecting 2 points. Slope of secant line is an average rate of change. If you see slope of tangent line, that means derivative. They have lots of ways to say the same thing. And all right. 2 equations, 2 unknown. Can we solve for a and b? What do we do? What do we do? Bump, bump.
Subtract the 2 equations.
Okay, so you can substitute, solve for one of the variables, plug it into the other. I like to try to cancel if I can. Can we cancel one of the 2 variables pretty simply by a nice combination? So a nice combination like multiply one equation by a number, maybe multiply one equation by another, multiply another equation by a different number, add them up. Our goal here, our philosophy, is 2 equations, 2 unknowns. Sure, all right, that can be done. But you know what's better? 1 equation, One unknown. That's the real goal. So, can we knock out a variable? And if so, how? Combined by how? Add them together. So we'll add the left-hand sides together. 5a plus 2a. 7a. b and minus b? No b. Minus 2 minus 5? Negative 7. So that's one equation you want to know. Like I said, that's much easier to solve. Do we know what a is? So a is negative 1. All right. Now, once you know what a is, just come back to one of these equations. Doesn't matter. Let's suppose we do this first one. We have minus 5. 5 times minus 1 plus b equals minus 2. Add 5 to both sides, and we get that b is 3. So a equals minus 1, b equals 3, and we already said c equals 10. So we found our ABC. All right. Any questions? They might have said, oh, I don't know if I would have necessarily seen like, oh yeah, I know what f of 0 is 10 and put it there. And it's okay. Even if you hadn't seen it, you could just still plug into the A, B, and C. It'll still work out. So.
Do we need to write that as an equation or
No. So that's a good question. So when you're doing a problem, make sure you know what the answer should be. So in this case, the problem said, find constants A, B, C. So the problem is to find the constants. So once you found A, B, and C, you're done. The problem might be, say, find the function f of x of this form. Then you say, okay, then I have to give it as the function. And if you want to be extra careful, because you're like, oh, I'm paranoid about these graders. Because some graders are better than other graders. And I just want to make sure I get, good grading. You could say, look, I already wrote c equals 10, but I'll do it one more time underneath, because you could be like, oh, just in case the grader has a hard time reading, I'll put them all together. So that's not a bad thing to do. And boxing is highly recommended. I know we say circle your answers, but realistically, boxes are better fits. Okay. The other question I had was about chain rule, and so I want to talk a little bit about the common ways the chain rule gets used. And so the chain rule is a very important rule, and you should know it implicitly. It's one of those things that you just want to make it automatic. So part of the challenge is we kind of assume that you can do things sort of right away, but we don't practice it. So one of the things that we assume is you can say, I recognize the inside versus the outside. So let's look at two common rules. So this is called the general power rule. It says the derivative of f of x to the power k is k f of x to the k minus 1 f prime of x. So in practice, the way that you do this is you say, oh, if I see something to a power, you say, well, I grab that power, you pull it down in front, that's where the k comes from, you subtract 1 from the power and then multiply by the derivative. Now, how does this work? Well, you have to identify what's the inside versus what's the outside. So in our case, if I have f of x to the power k, what's the inside function? It's f of x. What's the outside function? Sorry, you said what? I heard k, but what?
Just something to k.
Something to the k. Right? That's great. Well, you want to use x again, or should we change to another letter? U. Oh, excellent choice. Have you had calculus before? I can tell. Anybody who says, oh, what comes after x? U. Yep. They've seen some calculus, I suspect. You'll see why by the end of the semester. All right. So those are our functions. Let's talk about the derivatives. What's the derivative of f of x? Yeah, the derivative of f of x is the derivative of f of x. That's what f prime of x stands for. It's the derivative of f of x. What's the derivative of u to the power k? K u to the power k minus 1. That's just saying, hey, that's our general rule for x to a power or u to a power. Now we say, okay, we remember that if we have g of f of x, the derivative of this is the derivative of the outside, leave the inside alone, times the derivative of the inside. So this is our g prime. So what happens? We're going to plug in f prime. Sorry, excuse me. The inside is f of x, so that plugs into the u, right? Your g prime of f of x. So that's where you get your k, f of x to the k minus 1. That's your, this part right here is your g prime of f of x. This other part right here, well, that corresponds to your f prime of x. Now, the clue that this part corresponds to f prime of x is that it says f prime of x. It's a pretty strong clue. Very good clue. So anyways, what I'm saying when I say we don't often write it down is we almost never explicitly write down the inside is f of x, the outside is u to the k. It's one of those things that with practice you do without thinking. And that's kind of the goal, is you want to get to the point where the differentiation rules are just mechanical. You're not thinking too much about it. You're making sure that you're applying the rules correctly. You know, you're not just randomly writing symbols on the page, but you're not thinking too much about the process. Just let me run the rules, run the procedures. And derivatives in that sense are not too exciting once you get the hang of it, but you get lots of right answers. And we like right answers. Okay, so what happens for this other one? Well, the derivative of e to the f of x, what's the inside? F of x, again, what's the outside? E to the u. The derivative of the inside? F prime of x. What's the derivative of e to the u? It's e to the u again. And so same as before, we plug the inside, that's our f of x, into the derivative of e to the u. And so the thing is, you have to keep track of like, oh, I actually am taking a derivative. So that's why we have e to the f of x. It's not just that we wrote it down again. It's just the derivative of e to something is e to something. So it's e to that function again, then times f prime of x. So this part right here, that's our g prime of f of x. And this is our f prime of x. All right, let's try some things, shall we? Let's see, what can we do? Suppose we try e. How complicated do we want to get? What?
Could you go to multiple powers?
Multiple powers. E to the sine cubed of e to the x to the fourth. How's that? Is that sufficiently many? Okay, how many layers do we have in our delicious onion here? I think 5, yeah. It certainly has that smell, that fresh onion smell. Ah, all right. Now, I feel kind of bad I didn't throw a square root in here, but keep in mind that when we talk about sine cubed, that's really a shorthand for sine of e to the x to the fourth cubed. So know your notation. So because of the way sine cubed is written, sometimes it can be a little bit subtle when you talk about derivatives of sine to a power or cosine to a power. And it's an unfortunate artifact left over from trigonometry history. Okay. Well, we begin. So, our outermost layer is what? Yeah, it's e to something. So, when we're taking this derivative, we say, oh, if it's e to something, we just say, start by writing down e to that same thing. Okay, so e to that same thing times our derivative. So now we're focusing on the derivative of that part. What's the rule we're using? Yeah, this rule. It's something to a power. So times outside of the e, right? I'll even put parentheses just to emphasize it. So 3, and then the inside stays as is to the power 2. Okay, now where do we go? Well, now we're working on our next layer. Okay, so we're taking the derivative of sine. Now that's not one of the functions we mentioned, but that's okay. We can do things that aren't mentioned. What's the derivative of sine? Cosine. Cosine of what? E to the x to the 4th. Okay, where are we now? Well, we've worked our way in. We're e to the x to the 4th. So, what's the derivative of e to the x to the 4th? Well, it's e to something, so it's e x to the 4th. Then, what happens? We take the derivative of that. So, what's the last thing for us to write down? And is it the last thing for us to write down? Have we finished that derivative? Yeah. We'll throw a box. We didn't have to throw a box, but that feels box worthy.
What about the derivative of that derivative?
The what?
The derivative?
We could, but we'd have to stay late. If you were going to take the derivative, you can do it. See, the punchline about derivatives is you can take derivatives, and you just follow the rules, and you have to be really patient. If we were going to take the derivative of the derivative, what rule would we have to use? Product rule, in addition to chain rule. So we could do it. It would take approximately this much space, but we could do it. In the interest of time, or maybe for once I'll say, probably in the interest of paper. Let's not.
Where it combines chain rule, product rule, or chain rule and closure rule, but like not on a grand scale.
Not on a grand scale. I mean, if you're talking like not on a grand scale, I have a little space down here. I mean, you can do something really simple, such as, what's the derivative of cosine? Oh, let's practice. What's the derivative of secant x squared e to the 4x? That's a pretty simple low-scale one. I claim it uses chain rule. It actually uses chain rule twice, and it does use the product rule. Do you know what to do? Oh, that's a great question. Do we do product rule first or chain rule first? It's the chain rule first, right? Because when are we going to do the product rule? Well, we're going to do our product rule once we have a derivative of a product. But right now, we're currently asked to take a derivative of a function which has another function on the inside. So the outermost setup is a function in a function. So our first round is going to be chain rule. What's the derivative of secant? Secant tangent. Do you need to know that? Yes. Not just for today. Not just for tomorrow. but for the rest of time. You will know it for years to come. You'll tell your kids. You'll tell your children's children as you gather around the fires from the nuclear fallout. Let me tell you the story. Okay, so now here's the thing that can be a little bit disconcerting. The derivative of secant is secant tangent. It's not really two functions. It's just a single function. This just happens to have two parts to it, but it's a single function. So what goes into the slots here? The inside. And it's the same thing for both. So it's x squared e to the 4x, x squared e to the 4x. So now you are at this stage. You say, okay, I took the derivative of the outside, I plugged the inside in, now I have to take the derivative of the inside. So what's the derivative of x squared times e to the 4x? What's our rule? It's product rule. How do we know it's the product rule? Because it's a product, right? That was sort of the clue. If it's a product, you should use the product rule. Wow, that's why we came up with such great names for these rules. Okay, so product rule is everybody gets a turn. The derivative of x squared? 2x. And then the e to the 4x stays as is. Then we're going to add x squared, the derivative of e to the 4x. Now it's the e to the 4x's turn. 4 e to the 4x. Where did that 4 come from? Chain rule. Is it okay to put the 4 in the front? Yes. Yeah. That's the nice thing about numbers. You can move stuff around. Okay, and now what do you do? Yeah, you box it. You're done. All right. All right, we have some time. I finished the problems that people asked. So, do you have more questions? Things you'd like to talk about? Things you're unsure about?
There was not entirely able to explain it. So
Okay.
Not able to be pulled up. I just emailed you a screenshot of the question.
You emailed me a screenshot of the question.
Homework 04B, question 3.
Oh, classic homework for question 3. Okay. As we all know, it's like our favorite one. My gosh. Yeah. Let's see. Ha 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 ba ba bum. Do 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 do. This is like the smallest text. I'm an old person here. Okay, find the equations of the tangent lines. All right. Let me see if I can see this. So we have the curve y equals cosine x. And we want to find the tangent lines at x equals pi over 2 pi 3 pi over 2. Interesting. And graph the curve with some tangent lines. Okay, so let's talk about, are you asking about finding the tangent lines or? More so finding them. Okay. All right. Let me see if I can. Okay. All right. Okay, so I have a curve y equals cosine of x. Now, what does cosine x look like? Well, it looks like that. All right. Now, do we know what the derivative of cosine looks like? Negative sine of x. Okay, so that looks like the following. It's now I claim that there's, well, I claim that I'm a bad artist, but but there are some clues as to what's going on. So x equals pi over 2. That's right there. So what you can do is you can say, well, cosine of pi over 2 is 0. Negative sine pi over 2 is what? Negative 1. So there's a slope here of negative 1. So once you have a point and a slope, you can write the formula. You say, okay, y minus your y value, 0, is equal to your slope minus 1, x minus your x value, pi halves. So you say, okay, y equals minus x minus pi halves. But I want to point something out here. If I come down to negative sine x, what do you notice about negative sine of x there? Slope is minus 1, right? So this slope of being minus 1 says, oh, the derivative is minus 1. Notice here, what do you see? What's the slope? 0. So what should be true for its derivative? Should be 0. What's this slope? 0. So what should be true for its derivative? Now, notice here, what's true about the slope? It's positive. You know how to tell if a slope is positive or negative? Yeah. So positive slope, you're walking uphill. Negative slope, you're rolling downhill. So notice that where you have positive slope, you have positive derivative. So it actually makes sense that even if you didn't know exactly what the derivative of cosine was, you can figure out things like, oh, I'm 0, and then I'm negative, and I get very big negative, and then I come back to 0, and then I'm positive, and then I come back here to 0. So you get connections. And so you can see some nice connections, but that's not your question. Essentially, I don't know. I rambled. Let me stop here with that one. We have time for maybe one more question.
What about derivative for the square root, like f of x minus g of x?
Derivative of?
F of x over g of, I don't have like a specific number, but
You want quotient rule?
is that quotient rule? I'm not, vocabulary is not my strong suit, I just know what things are.
Okay. So how do you do that? Derivative of f of x over g of x? Or you want to make it more complicated?
Like in a, no, like f of x minus g of x, both under a square root.
Derivative of the square root of f of x minus g of x?
Yeah.
Okay, so what rule do you need to have here? Well, first thing, if you have a square root, what do you do with it? Put it to the 1/2 power. Because you make it convenient for the tools we have. So it's a chain rule because it's something to a power. So what happens with this half? Comes down. F of x minus g of x, the inside stays the same. What's the new power? Negative 1/2. 1/2 minus 1. Times f prime of x minus g prime of x. And there we go.